Okay. Well, when I look at chapter 5, ostensibly we are at section 5.4, which is called what, integration formulas and the net change theorem. To be honest, that's not the most important or interesting thing. I mean, there are some problems in there that are just more experience with doing integrals, and that's a good thing. The net change theorem turns out to just sort of be yet another way of saying definite integrals, which was yet another way of saying the fundamental theorem of calculus. I feel like we've already had like 3 days about basically that exact same thing, just formulas slightly rearranged. And so today, I'm not going to spend time lecturing about section 5.4. In fact, I'm only giving you 3 problems from that, and they're basically just definite intervals. Okay, we can do it once the cameras are done rolling or whatever. But I think actually what we learn in the next section, which I think is 5.5, substitution is both more interesting and more useful, and dare I say it, more fun. So we're going to do just a teensy bit of section 5.4 just so we can check it off the list of things we accomplished in our class. But we are mainly going to focus on section 5.4. Now, section 5.4 is this neat method of substitution as a way of solving some kind of integrals, whether definite integrals or indefinite integrals. Remember, indefinite integrals are the one where you've got like an integral symbol, some stuff, dx, and the answer to that is going to be some kind of function plus c. Because it turns out, I mean, remember, what is this? That means that the derivative of this function over here could be this. And it turns out, well, any constant you added over here, once you took the derivative, that would go to 0. Or we could be talking about definite integrals, where you're integrating from like a to b, where these are maybe numbers of some function dx, and you get some antiderivative of it evaluated at b and a. In other words, you take that same function at b minus that function at a. Those are the definite integrals. All right. And we've had a small table somewhere along the way of some of the basic integral formulas. Things like the power rule, or the integrals of sine, cosine, and a few such things as that. But based on those tools, there are lots of integrals that are possible, but you got to have tricks to figure out how to prove them and so on. But one of the techniques that you can use to evaluate lots of integrals that look pretty complicated is called the method of substitution. Method of substitution. Close enough. All right, let me give you an actual problem that's in this chapter here. This happens to be, for example, 5.30. And here it is. It is the integral of 6x times 3x squared plus 4, 3x squared plus 4 to the 4th power dx. Oh man. Now that particular thing just looks like something that would come out of a math textbook. But it could be that that is like a physical formula for something that's describing the motion of some charged particle, or that's describing the rate at which some bank account is increasing under some method of compounding interest, or whatever. Now, one thing you could do, which would be horrible, is you could just expand this out. You could take the 4th power of this, write this all out as 6x times 3x squared plus 4 times 3x squared plus 4, and FOIL the heck out of all that, and have some horrible looking equation, but it would just be the sum of a polynomial. It would just be a bunch of terms with like x to the 8th power, and x to the 7th power, and and it would be a big mess, and frankly, the odds of making an error are pretty high. But you could do it, okay? But that's not a good trick. We're going to use the method of substitution to solve this bad boy pretty easily. For reasons that I don't know, the symbol we tend to use when we are doing a substitution in these kind of problems is U. Now, if you actually go look in section 5.5, they actually have like a box with highlighting and all that kind of stuff that explains, like gives the dictionary definition of method of substitution and so on, and it shows how it's like a posit function. You know what? That's all lovely, and then they even prove it. Here's the deal. No, let's just learn how to do it and solve problems with it. And the idea of method of substitution is to find a way to rewrite this in terms of a new variable. We're going to come up with a new variable u that is equal to something. related to x. I'm going to, now your book actually calls it, I think, g of x. We're going to come up with some kind of so we're going to come up with some kind of function of x that is going to be u. And we're going to make a substitution. But in order to do that, we also need to know the derivative of u. The derivative of that u with respect to x. I mean, we're going to have to be able to take that derivative there. Notice the notation I'm going to use here. And the reason why I'm going to do this here, where I use instead of writing u prime, I wrote du dx, is because I'm going to take that dx over to the other side. So when we do some substitution, we're going to be using this to get rid of this part, and we're going to be using this u to get rid of stuff over here. Let's do an example of that using this right here. Now, in some of the problems you're going to be doing on the homework set, they give you what that substitution is, and they want you to walk through how to do this problem. In other cases, you have to figure the substitution out yourself. Now, you have algebra, trig, pre-calculus type classes in your life where you have discovered that sometimes that's hard. Factoring. When you did factoring, to some extent, it's trial and error. And the same is true generally with these, but we can start finding some patterns. But for this first example, let me just tell you that I want u to be equal to that part that's in parentheses, 3x squared plus 4. That is my substitution. Then, I can see now already, this is like u to the 4th. That seems handy. But I've still got this thing out here. And I got a dx here. But I told you we had to find the derivative. du dx. The derivative of this with respect to x is 6x dx. Oh, sorry, is 6x. Right, that's its derivative. That means I can make I can put that dx on the other side. du equals 6x dx. Look what's left over on my function over here. Once I made that u substitution here, all that was left was 6x dx, right? U to the 4th, 6x dx. Well, 6x dx equals du. So the integral of all this xy stuff right here is also the same thing as the integral of u to the 4th du. That's not hard, right? U to the 4th is an easy one. It's a power rule integration. Power rule integrations, remember, all we do is increase the power by 1 and then put that 1 over that power out in front. So the integral of this is 1/5 u to the 5th power plus c. Or we can now put that back in there from that u definition where u is equal to this. So that is 1/5 3x squared plus 4 to the 5th power plus c. Let me just double check if that's the answer they got on problem example 5.30. And yeah, they wrote it in a slightly different form, but that's the same answer. See how by finding a clever choice of how to do that substitution and popping that in instead, we got the integral into a way, way simpler form. Notice that in order for this to work, we had to get rid of every x. It's not okay to leave some of them behind. Your final thing has to only have, which when you're ready to do the integral, has to only have those. If you're going for the substitution, you got to go all the way. Okay? Get every x out of there, which might mean you have to make pretty good choices about what you're doing with that, what your value of that u is. Let's see if we can make another quick example here. That's a proof. I don't know that we want to do that. Well, this was quite similar, but that's okay. We'll do a similar-ish one. This is the one that they're talking about right at the very beginning of the chapter, the section rather. And they're doing the integral of x squared minus 3, all raised to the what power? 3rd, times 2x dx. Okay. Again, in some of the problems, they're going to give you the substitution, and in some you have to figure it out yourself. Let's keep playing the game of we're pretending we're going to do these where they've given it to us. I'm going to give you here that the substitution u is x squared minus 3. So right off the bat, I can see this integral, he's just got a u cubed in there. Because this is my u, so it's u cubed. Now that derivative of this thing over here, with respect to x, is just 2x. Or we could take that dx over to the other side, 2x dx. And well look, that's what was left. U cubed, and we still had this 2x dx, but that's what du is. So we have changed that whole messy integral with respect to x into just u cubed. Well, that's an easy integral. That's just 1/4 u to the 4th power plus some constant, or 1/4 times x squared minus 3 to the 4th power plus c. That's not so bad. A surprising amount of real integrals in the real world, like when you're evaluating the position of some particle in a physics class, or in an engineering problem where the force is acting on some girder, or some business problem. A surprising amount of time, this is the technique you use. It seems like it would be kind of a weird coincidence that this would work, but a surprising amount of time, this is the technique that will get you the answer. Now, sometimes you have to kind of, sometimes you kind of have to make it fit. You kind of do a little wiggling to make it fit. One size fits all. And then you got to pin it back here. You know what I'm saying? All right, you got to adjust the straps a little bit. All right? For example, I think your book is calling this substitution with alteration. Let me see if I can find an example real quick of that. Let's do a substitution by alteration. How about the integral of x times x squared minus 5 to the 1/2 power dx. In your actual book, in the problem in the book, it's z's, but whatever. I wanted to keep it simple. Okay. Overall, this doesn't look, I mean, it looks like the kind of pattern we keep seeing. You know, there's sort of a little function in here, and we're going to do the substitution about that. A good hint to be looking for, notice, whatever we use as u, the part that's left should be one order smaller. So like this is x squared, and this is x to the 1st power. That's always a good thing to be looking for. Because, remember, you're going to have a u, and then you want the rest of the stuff to work out to du, the derivative of it. So right off the bat here, I can see that this guy's going to need to be u is equal to x squared minus 5. So the derivative of u with respect to x is just 2x, or du equals 2x dx. Okay. So let's make that work. Over here, clearly I've got, this is my u, so this is u to the 1/2 power. I've got x dx left over. But notice the derivative of u is actually 2x dx. I got to kind of pin it together. I got to kind of find a way to alter this to make this work out. I mean, what I've got left over here is x dx, but actually over here I've got 2x. Well, if I divided both sides by 2, or multiplied both sides by 1/2, 1/2 du equals x dx. Do you see how I had to kind of switch that over there? So x dx equals 1/2 du. Oh, x dx equals 1/2 du. Or 1/2 the integral from u to 1/2 power du, 1/2 times, oh boy, u to the 3/2 power 2/3 plus c. Looks like this is 1/3 times x squared minus 5 to the 3/2 power plus c. Just out of curiosity, is that right? Yeah, this is the right answer. Everything I've shown you so far has been for an indefinite integral, where I don't have those limits of integration at the top and bottom of the integral symbol. And that's why we kind of keep adding c over here, because they were indefinite integrals. What if we had the same sort of problem, but it was a definite integral? We had limits of integration on the ends there. Let me see if I can come up with a problem. Let's say it was the integral from 0 to 2 of x times x squared plus 1 to the 6th power dx. Now, again, let's think about what we want our substitution to be. That u that we choose needs to be something so that when we do du dx, we get the rest. And so since we're going to be taking the derivative, we're expecting the power to go down by 1. So notice how u is right here. As if we took u as this thing here, u is x squared plus 1. The derivative of that will have an x in it. So in this case, u is x squared plus 1, du is 2x, so du equals 2x dx. Well, that's not exactly what we've got here. We've got u to the 6th power. We have x dx, not 2x dx. If we multiply both sides by 1/2 again, we get that. Now, what I want to show you, though, is I've got a problem. What to do with those limits of integration? Now, when we wrote 0 here, or when we wrote 2 here, a better, more complete way to have written that would be to have written that as x equals 0 and to x equals 2, because we are integrating with respect to x. We are starting at x equals 0 and going until x equals 2. That is the range along the x-axis that we are computing the integral along, that we're finding that area under the curve. We can't just put 0 and 2 right here now. We need this to be integrating u equals something to u equals something. There are 2 happy ways to play this game. One happy way to play this game is to go, okay, wait a minute. If x equals 0, use my formula back here as to what my substitution was. If x equals 0, 0 squared plus 1, u equals 1. And if x equals 2, 2 squared plus 1 is 5. So one way to do this would be to now use the you got to use the substitution on the limits of integration as well. Now we can have our happy integral here. That's 1/14 u to the 7th power evaluated from u equals 1 to u equals 5. So that would be 1/14 times 5 to the 7th power minus 1 to the 7th power, which I don't feel like computing right now. It will be a big number. Remember, I just made up this problem. So this is one happy way to do it. One happy solution. Where you go ahead and you figure out what the values over here of u that are the new limits of integration. And that's okay. Or, which is not the way your book does it, this is the way Father Ports taught me back in Calc 1 175 years ago. Another way is to forget about the limits of integration for a little bit. Just do your substitution. Do your integral. Now, where that u is, put the x back in there. From x equals 0 to x equals 2. Put that back in there. So this is 1/14 times, plug in the 2. Let's see, that would be 5 to the 7th power minus, now plug the 0 in there, 1 to the 7th. Hey, wait a minute, these things are the same. As well they should be. Right? So either, once you've done the substitution, and you've figured out how to do the substitution here, substitute on those limits of integration. That's good. That's happy. And just do the integral and never look back. This would be the never look back. You never again think about x's this way. You're all back into the land of u's. Okay? This is, you're just sort of using the negotiable favors of the value of u. But as soon as you get out of that integral, you get back out of those u's and you go back to x. Okay? You're sort of just borrowing the niftiness of u for a second there, and as soon as you get out of that integral and you're done with them, you just get rid of that u. You put them back into x. The reality is, like in fancier classes, Calc 2, Calc 3, Vector Calc, etc., turns out both of those techniques are good. Right now, when we're doing relatively simple calc problems where there's just numbers for like what's at the limits of these integrals and stuff like that, either of these techniques is equally happy. It turns out later, it gets worse. It turns out in later calc courses, these limits of these integrations themselves might be equations or functions or whatever. Yeah, then things get messy. But we're not there. Substitution is in many ways one of the most powerful things you learn when you're doing integrals. There are lots and lots and lots of problems where this turns out to be the way to solve these problems. Let's get one more before we get too far on these guys. I'll do an even numbered problem. How about 276? The integral of sine to the 7th power cosine. Sine to the 7th power of theta cosine theta d theta. If u was equal to the sine of theta, the derivative of u with respect to theta would be cosine theta, or du would be cosine theta d theta. So this would be the integral of u to the 7th power cosine theta du. Well, heck, that's no big deal. 1/8 u to the 8th power plus c, or 1/8 u sine to the 8th power theta plus c. Hey, yeah, that substitution could involve trig functions. Sometimes it does. All right. These problems are nice little exercises. They're not terribly hard. Most of them, they give you the substitution. So, here's the deal. On previous section, 5.4 or whatever. Again, just so we can check off on the box that we did it. Page 575. There's like 3 little integrals. What are their numbers there? 207, 209, and 211. The rest of that section is actually pretty much just different ways of saying fundamental theorem of calculus yet again. I don't think we need to do that yet again. And then go forward into today, which is page 592, and you would do 261 to 281 odd. Which again is not exactly a huge assignment. I mean, that's only like 10 problems or 11 problems, something like that. Alright, I think that'll do it. And yes, I think we're good. Alright, I'll go ahead and stop this and start it uploading.